Okay, this is our 3-wire circuits with line conductor resistance included, part 2. What we're going to analyze here is what would happen if we had an open neutral circuit. Alright, an open neutral would be a bad connection in our neutral situation here. And if we had a balanced 3-wire circuit, we know that the results of that open neutral wouldn't impact the circuit anywhere near what it's going to happen if we have the unbalanced 3-wire circuit like we currently have here. Okay, so before I make the break, it's important for us to figure out what the resistance of these loads were prior to that break happening, because we're going to need that information in order to solve for the actual voltage drops that will occur. Alright, and we do that by looking at the current as it was normally operating divided by the voltage drop that we actually calculated. So we've got the 2 amps divided into the 120 volts on that first load, alright, and that gives us 60 ohms. And down here we've got 119.4 divided by our 4 amps, which will give me, and I can't do that one in my head, so I'll pull out my calculator. I've got 119.4 divided by 4 amps, and that gives me, let's just double check my math here, 29.85. So not exactly a rounded number there, okay, but that's an accurate number. So we're going to need those values of resistance in order to solve for what will end up being a new circuit here. Okay, once we open this neutral up, okay, we no longer have the ability for the 2 amps to be coming out of that neutral to balance this out. So what we're left with is this resistance plus that resistance plus that resistance plus that resistance across our 240 volts. So we're going to have to look for a new impact of that circuit. Okay, if I redraw it, quite simply, we're going to look at, we've got our line resistance, we've got our load 1, our load 2, and our line resistance there with no neutral. Okay, so this was our 60 ohms, this is our 29.85 ohms, and these were each 0.1 ohms. So my R total for this circuit will end up being, we've got the 60 plus the 29.5 giving us 89.85 plus the 0.2. So what is that going to be? That's going to be 90.05, I think, but I'll double check the math. Okay, so we've got 29.85. We're going to plus that 60 plus 0.2 gives me 90.05. I was right. 90.05 ohms. Okay, we're going to divide that into our source voltage of 240. Okay, and that'll give me a new line current. So I'm going to take that 240 divided by, and that gives me a new line current of 2.665. So that is my new line current now. Okay, so we're going to take that current, we're going to multiply it by each of these guys. So we know the 2.665 times the 0.1, okay, will give us 0.2665 volts there, and 0.2665 volts there. All right, but then it gets a little bit more complicated here with these ones. So we're going to take that current, I'm going to store it, we're going to multiply it by 60, and that gives me a voltage there, look at my glasses here, of 159.91. Okay, so that's far and above what the original 120 was there. Okay, so that's not going to be very good. All right, and then I'm going to hit that current again, and I'm going to multiply it by 29.85 to give me 79.556. I'll call it 79.56. So that's that voltage, plus we have our line conductors as well. So at the end of the day, we always ask you what would be the voltage drop across that break, if we were looking at it in a metered sense, I'm just going to get rid of some of this stuff here. Okay, so keep in mind that a lot of this has changed now. I'm just going to try to simplify things out for you guys a little bit as a drawing goes. Okay, so we would look at, we've got no current there. Okay, so what is this meter going to read? It's going to read the difference between 120 minus that plus that added together. So the 159.91 and 0.2665. 159.91 plus 0.2665 is 160.018. 160.018 volts. Subtract 120 from that, and we get a difference of 40.17. Whoops, not there. Okay. We could also look at the difference between 120 subtracting these two values here, the 79.56. 79.56 plus our 0.2665 gives us 79.8265. Subtract 79.8265, and we're going to subtract 120 from that, and that is 40.17. Same value there. Okay? So when you're dealing with open neutral circumstances in an unbalanced 3-wire that has line resistance included on it, you need to solve for it like it normally would have been operating. Okay? Solve for the resistance of the loads as it was normally operating. Do the break then, and with that create our new series circuit across 240 volts, figure out our new current based on the resistance of that total circuit. Okay, with that new current, go back, solve for new voltage drops, and then take 1/2 and subtract it from the 120, or 1/2 subtract it from the 120 to get our voltage across the break. Okay, so it's pretty much the same process we've done in the past. The only difference is now you got to pay attention to the line conductors in there too, and they do incrementally change the way that the circuit works a little bit. Okay, not a massive impact with 0.1 ohms on each of them, but enough that your answer, if you neglected these ones, your answer would end up being out a little bit compared to what we were looking for accuracy. All right, so that is a 3-wire circuit open neutral situation with our conductor resistance included. And that's the end of this video.